Good morning. We're going to finish up the section on geometric sequences and series now by switching from sequences to series. A sequence, again, is just a collection of terms, and now we're going to switch to series, which means we're going to start to add those together. So again, the big key, when we go to series, we're summing, adding up the terms in a sequence. So for a geometric sequence then, the definition would be the sum of the terms in a geometric sequence. All right, and so the formula I'm going to need everyone to work with is this one, S sub n. Again, S we use to stand for the word sum. N represents the number of values that we're going to combine, that we're going to add together. And what that's going to be equal to is a sub 1 times 1 minus r raised to the n power divided by 1 minus r, where a sub 1 is the first term in the sequence, and r, both here and here, is the common ratio. All right? The most common mistake when applying this formula, though, isn't the A1, it's not the R, it's the power that's attached to the R in the numerator. And what I need you to notice is that however many terms we're being asked to add together, that's exactly the same as the power that we use on the R, right? Those values are the same. The most common mistake is to make this power, if you can see the arrow, make this power one smaller than the number of terms we're asking you to add together. But with this formula, however many terms we're asking you to add together, whether it's 10 terms, 15 terms, 100 terms, this power is exactly the same. Okay? So make sure you get that formula into your notebook. And now let's try a few examples. As an example, if I were to give you this infinite geometric series, I'm going to ask you guys to find the 10th partial sum, which means add up the first 10 terms. Okay, so we're going to be finding the sum of the first 10 terms of that series. Now please notice this is geometric. It's geometric because if we take any term and divide by the one that comes before it, we get the same number, a common ratio. 54 divided by 18 is 3. 18 divided by 6 is 3. 6 divided by 2 is 3. We get a common ratio. Okay? So to find the sum of the first 10 terms as an example, what we need to do is start with the very first term, which is 2. And above, I'll just give you the part of the formula I'm filling in. So in this case, a sub 1, the first term is 2. Then we have to multiply by 1 minus the common ratio raised to the 10th power. Please remember, whatever number of values we're trying to add up, the power is going to be the same. All right, and then we're going to divide by 1 minus r. So we're going to have the value for r here and the value for r here. And again, please remember you find r by taking any one of the terms and dividing by the one that comes before it. So I'll do it off to the side here. So we could take 54 and divide by 18, or 18 divided by 6, or 6 divided by 2, but no matter which pair we pick, when we divide, we get a common ratio of 3. All right? And then we just have to do the arithmetic here. We also have to work inside parentheses first. Inside the parentheses, we'll have to perform the exponent. So I'll have to raise 3 to the 10th power, which is 59,049. Then subtract inside the parentheses 1 minus 59,000 and, whoops, sorry about that, and 49 would be negative 59,048. Downstairs 1 minus 3 is negative 2. And then when you multiply and divide, essentially the 2's cancel and the 2 negatives make for a positive answer. What we'll get then as a result for the sum of the series is positive 59,048. Okay, What's interesting about this formula, by the way, is that we're able to find the sum of the first 10 terms without having to know what the 10th term actually is. We don't need to know that. With arithmetic series, we needed to know what the last term was, but not with geometric. Okay? A couple more examples then. Here's an example given in terms of summation notation with our sigma, and this is going to be geometric. Now I need you to pay attention here. Whenever something is given to us in sigma notation, we're going to know it's geometric if the equation is exponential. If the equation attached to the summation is exponential, that implies that the series will be geometric. Really important. If the formula is exponential, it has a variable in the exponent, then the series is going to be geometric. Okay? So therefore, we can get to the sum of these 7 terms in this series by taking the first term times 1 minus the common ratio raised to the 7th power divided by 1 minus the common ratio. So what I need to find the sum is I need A1 and I need R. Okay? Does everybody see A1 immediately from the problem? No. So what we're going to have to do is actually start the summation by replacing n with 1. So if I replace n with 1, my first term then is going to be 2 to the 0 power, and 2 to the 0 power is 1. My second term would be, now put in 2 for n, and of course you could keep that going if you wanted to. My second term then would be 2 to the 2 minus 1, or 2 to the first power, so my second term would be a 2, and I could keep that going. Okay? But I was able to find the first term, so I have A1. The other value I need is R. And again, I just need you to pay attention to this part. R is always going to be equal to the number base. So again, in summation notation, this is going to be geometric anytime the formula or the equation is exponential, and then whatever the number base is, that's going to be the common ratio. So the 2 here is going to be the R, the common ratio in our formula. So we'll have a common ratio of 2 there and 2 there. And again, all I need you guys to do is perform the arithmetic. Inside the parentheses, do the exponent. 2 to the 7th power is 128. 1 minus 2 is negative 1. 1 minus 128 is negative 127. And 1 times negative 127 divided by negative 1 would be positive 127. Okay? So I have a couple of important things. If the formula is exponential, that means it'll be geometric. And if it's geometric, then the number base is the common ratio, the R in our formula. So with that in mind, let's try 2 more of these. All right, another one in summation notation. Is this an exponential? Yep, because we have a variable in the exponent. So that means it's geometric. And whatever the number base is, that becomes the common ratio. Okay? So the 2 is not the common ratio, the 0.1 is. Therefore, the summation is then going to be, the summation of these 20 terms will be the very first term times 1 minus the common ratio raised to the n power. So the common ratio we can see clearly now is 0.1. And then we're going to divide by 1 minus r. And again, the common ratio is 0.1. So the only thing we're missing then is the very first term. And how do we find the very first term? We find the first term by replacing n with 1. We do not need the second term, third term, fourth term, or even up to the 20th term. We don't need any of those. We only need the first term. Okay? And so to calculate that, 0.1 raised to the first power is 0.1, and 2 times 0.1 is 0.2. Okay, and now we're set to go. Now we'll have 0.2. Inside the parentheses, we have to do the power first. Oops, sorry about that, that's a typo. There we go. So we have to raise 0.1 to the 20th power, and of course that's going to be just crazy small. It'd actually be 10 to the negative 20th, 1 times 10 to the negative 20th power. But if you consider your sig figs, that's essentially the same as 0. So what we'll have then is 0.2 times 1 divided by 0.9. So it'd have 0.2 divided by 0.9, which is 2/9, or if you prefer the decimal, 0.2 repeating. Okay? And I've got one more set up to go. This one's a little bit on the tricky side. This one's a little bit tricky. I'm just going to give you like a 10-second head start. Why is this one trickier? Please take a look, see if you can see what I'm talking about. There's something that makes this one a little bit tougher than the previous couple. Were you able to spot it? Let me get going and see if you can find it. Again, we want to add up all of these terms, but my question to you guys is, how many terms are we asking you to add up? Right? It's real easy to say 10 because the top number on the summation is 10. So it's real easy to say, well, numbskull, we're adding up 10 terms. But are we? No. If we started at 1 and went up to 10, of course that would be 10. But here I'm trying to trick you a little bit. This time I'm asking you to start at 0. So if we start at 0 and go up to 10, I'm not asking you to add 10 terms. I'm asking you to add 11 terms. So I've got a deluxe eraser, my subscript there. And so instead we're going to actually be adding 11 terms together. Okay? So once we understand that, then the rest of it is the same as the previous examples. We need the very first term, and we get the first term. Whoops, hit something on my screen there, sorry. There we go. I get my first term by actually replacing n with the first value. And the first value that goes in for the variable is 0. Again, we don't care about the second term, third term, fourth term, fifth term, any of those. We just need the first one. So 1/2 raised to the 0 power is 1, and 16 times 1 is 16. So the first term is going to be 16. Then we're going to multiply by 1 minus the common ratio raised to the 11th power. What's the common ratio again? The number base on the exponential. So the number base here is 1/2. And then divide by 1 minus the common ratio. Okay? So here we go with the math. Again, inside the parentheses first. 1/2 to the 11th power is 1 over 2048. Downstairs, 1 minus 1/2 is 1/2. Then subtract 1 minus 1 minus 1 over 2048. So that's going to then be, 2047 over 2048. And then we're dividing by 1/2. And if it's okay with you guys, what I'm going to do is take this 1/2 in the denominator, take the reciprocal, and multiply the top by 2 over 1. All right? And I hope you'll see that we have some canceling then. The 16 and the 2 that are in the top will cancel with the 2048 down below. And when I do that canceling, I'm left with 64. So it'd end up with 2047 64ths. Okay? And of course, you guys could punch this out as a decimal if you wish, but since it's exact, I'll leave it as a fraction. Okay? Alrighty. So those are basic geometric series where we could add up 11 terms or 20 terms or 7 terms, however many you might happen to have. But what's kind of neat is we can extend beyond that a little bit, and we can actually calculate, in certain cases, we can actually calculate infinite series, meaning we can add up an infinite number of terms. Now there's some restrictions that have to be true for this to work. First of all, we can do it with certain types of geometric series. Not all, but only certain types of geometric sequences. We can actually add up an infinite number of things. And this is going to work, and this will be important to jot down. In fact, let me be more specific. I'll use the word only. This is only going to work when r, the common ratio, is less than 1. When the common ratio is less than 1, then part of our formula that we've used on the previous couple of examples, right, here's my formula I've used for the previous couple of examples. And now if we make this sum infinitely large, so instead of 7 terms or 20 terms or 11 terms, now we're going to add up an infinite number of terms. Now I'm going to replace, let me get it down here, and choose my laser pointer. Now what we're going to do is we're going to make this power infinitely large. And when r is less than 1, so think of something nice and easy like 1/2 or 1/3, you know, something nice and easy like that, 1/2 or 1/3. When this r value is smaller than 1, so it's something like 1/2, and we raise it to the infinitely large power gets bigger and bigger and bigger and bigger and bigger and bigger, then what happens is this term, let me circle it up in red, this term gets closer and closer to 0. Excuse me. So what happens then is our formula becomes a1 times 1 minus 0 divided by 1 minus r. But what is 1 minus 0? 1. And when we multiply a sub 1 times 1, we get a sub 1. And so in the specific circumstance, when r is less than 1, so when this is the case, when r is less than 1, then we can add up an infinite number of terms in a geometric series, and it's just simply going to be equal to a sub 1 divided by 1 minus r. That's all we're going to have. And so the formula for an infinite geometric series actually turns out to be nicer, easier than the finite. Okay, so let's try a couple of examples of those. Let's just try a couple of examples. As an example, if I were to give you these terms, 8, 4, 2, 1, and so on, but make it infinitely big, could you guys calculate that infinite sum? And the answer is going to be yes, only if r is less than 0. And what's my r value here in this problem, guys? R is going to be equal to, take any one of the terms and divide by the one that comes before it. So if I take the 2 and divide by 4, I get 1/2. Question, is that less than 1? Sure. Therefore, I can add up the infinite number of terms by taking the very first term, 8, and dividing by 1 minus the common ratio. And the common ratio here is 1/2. So when I actually do the arithmetic, which is much easier this time, 1 minus 1/2 is 1/2, and 8 divided by 1/2 is 16. The sum of the infinite number of terms then is 16. Okay? And you might think, really? Is that really going to work? But if you think about it, when you add up the first 2 terms, we get 12. When you put on the next term, we get 14. When you put on the next term, we get 15. If we were to do maybe just a couple of more, put on the next term, we'd get 15.5. And let's do one more. I think you'll probably get a feel for it. The next term would be 1/4, so we'd get 15 3/4. But if we keep that going, we're just going to keep getting closer and closer and closer and closer and closer to 16. And next year in calculus, I'll prove something to you guys in the fall that if we make this series infinitely large, it actually does equal 16. Okay, so kind of a fun idea that we can think through for something that maybe a week ago or 2 weeks ago would not have seemed possible. All right, let's just try a couple more examples with the same idea. I'm just going to give it to you in a slightly different fashion. So I'll give it to you as a summation. So if I give you the summation from n equals 1 to infinity of 5 times 0.2 to the n, can we calculate this infinite? Notice on the top of the summation is infinity. Can we calculate the infinite summation? And the answer is going to be yes, only if r is less than 1. Now, first of all, is this going to be geometric? Again, yes. It's geometric because the variable's in the exponent, so therefore we have an exponential. And then when we have an exponential, the r value is going to be the number base. So r here is going to be 0.2. And since 0.2 is less than 1, we can calculate the infinite series. How do we do that again? We take the first term and divide by 1 minus the common ratio. Let me write it down again on this screen so it's right in front of you. All right, so what we need is the very first term. Gosh, we don't have that laying around. So we go back up to the summation, and I have to replace n with 1. We don't need the second term, we don't need the third term, we only need the first term. All right, so 5 times 0.2 to the first power, 0.2 to the first power is 0.2, and 5 times 0.2 is 1. And then we have to divide by 1 minus the common ratio, which is 0.2. So 1 divided by 0.8 is going to be equal to 1.25. Or if you preferred the fractions, 5/4. So whichever form you'd prefer your answer in. That would be the infinite series. Okay? And let me just jog through one more and then we'll call it a day, call it a section. All right, one more in summation notation. So n equals 1 to infinity, so again an infinite summation. And this time we'll have 2 times 0.4 to the n minus 1 power. Can you guys calculate that infinite series? Again, yes. First, this is geometric because it has a variable in the exponent, therefore it's exponential. When it's exponential, the number base is the common ratio. And since 0.4 is less than 1, we can calculate the infinite summation. Okay? And so what we need again is the very first term. In fact, I'll write this out one last time. So we need the very first term. And again, we don't have that in front of us, so we need to go to the summation and replace n with 1. All right? Again, we don't care about the second term, third term, fourth term. We just care about the first one. So we'd have to subtract 1 minus 1 in the power. 1 minus 1 is 0. 0.4 to the 0 power is 1. And 2 times 1 is 2. And then again, the common ratio is the number base, so 0.4. So when we subtract 1 minus 0.4 is 0.6. And if you were to punch this on your calculator as a fraction, it would be exactly 10/3. If you'd rather approximate, it's going to be 3.3. Again, so please decide for yourself which form you'd prefer. Okay, so that's the end of section 3. There might be a question on a couple of the problems, but again, feel free to communicate with me by email or phone. I can help you out the best I can with any of the problems that you have on your 10-pack. Otherwise, I hope you're having a great day. I hope you're having fun doing some math at home. I know it's not the same as being together, but hopefully we'll be together again soon. Have a great day. Bye.